elemental thrust for linear twist and ideal twist. Today what we will do is we will look at these two expressions, that is the torque coefficient and the power related to the rotor. Now, we have made all the approximations, small angle assumption, and the elemental torque is number of blades L into phi. Phi you know is the induced angle, and then D is the profile drag coefficient. Okay. So, this has two components, one comes due to lift, another one due to the profile drag of the airfoil. That is why this particular term later we will say this is actually induced drag and this is the profile drag. When you look at the power expression, it is exactly same, only thing is there is a omega, because power is torque into omega, and again this has the same component. So, the power required now has two components, one is due to the induced power, another one is the profile power or profile drag power. Now, there are two components to the power part. Okay, now, let us write the expressions. After that, we as usual we non-dimensionalize the whole expression, which is because we take dq is n, you are substituting for the lift and the drag. Lift is, we wrote it half rho u t square card and then lift curve slope into theta minus phi. Phi was written as up over ut into, there is a another factor phi which is again up over ut plus the drag term, which is essentially half rho ut square c c d, okay, into r d r. So, this is my torque, elemental torque due to all the blades in hover. Now, if I want the total torque, I have to go integrate over the length of the blade. So, I will put 0 to capital R, this is Q, and power is exactly just because this is the same expression, there is a omega and omega is a constant. Okay. So, power is Q into omega, that is all. Okay. Now, what we do is we write the expressions in non-dimensional form. So, non-dimensional CQ, which is the torque coefficient, this is nothing but Q over rho pi r square omega r whole square into r. This is the torque coefficient, and you will look at power coefficient, Cp is power divided by rho pi r square omega r whole square into omega r. Okay. All right. But you know that power is q omega. Therefore, omega omega will cancel out, leaving behind you will simply say Cp is equal to Cq. So, power coefficient the coefficient, not the power is same as torque. Okay. Power coefficient is same value as torque coefficient. That is why when we evaluate, we never use CQ, we directly go for power coefficient, okay, because Cp equals Cq. So, straight away write all the power expressions. Okay. Now, let us non-dimensionalize this. Is it clear? Okay, because power coefficient, torque coefficient both are same for rotor under constant RPM, please understand, because omega is constant, otherwise you will get an instantaneous thing. Now, let us write the CQ. You have to divide by rho pi r square omega r whole square into r. So, non-dimensionalize this, and you know that ut is omega smaller, and u perpendicular, if there is a climb, we used it as Vc plus nu, right. So, non-dimensionalize with respect to capital omega r. So, this will become just r bar, r over r. This we call it as lambda. Okay. So, we will call, if you take this, rho will cancel out, then of course, you will get NC over pi r, that will be sigma solidity ratio. Okay. You will get in non-dimensional form, and I am going to write that in non-dimensional form. So, I write CQ directly. Okay. Since you know CQ is Cp, so this is in non-dimensional form, the value becomes sigma A over 2 lambda theta r bar square lambda r bar, okay, plus sigma C d over 2 r bar cube d r bar. This is the expression. Okay. Now, if you split this term into two parts, we can write it in, this is one term, this is another term. If I write this, it will be 0 to 1 sigma A over 2 lambda theta bar. Okay. We had one, what is that? We have to take an r square, r bar square minus lambda r bar into d plus 0 to 1 sigma C d over 2 r bar cube d r bar. Okay. Oh, sorry. Now, if you look at this particular expression, leave out the lambda. This is nothing but differential of thrust coefficient, because if you look at that earlier last class I derived sigma A over 2 theta r bar square minus lambda r bar d r bar, I wrote it for integral, that is Ct. Okay. Is it clear? So, this term you can write it as simply lambda dCt, because differential of thrust coefficient, because lambda is this. If you look at this term, last class we got, that is the dCt, and this is of course sigma Cd over 2 dr bar. Okay. Now, this is Cp. we have split the power expression as we did the component due to thrust, the component due to profile drag. Okay. And even this term can be further divided into two parts, because that is, I go back here, okay. You can write this as, because lambda we said Vc nu over omega r. This particular term is lambda c, this term is lambda I. One is the climb, another one is the induced. Okay. So, I can again put it as lambda c dct plus integral lambda I dct plus of course, the profile drag. Okay. All right, is it clear? Now, you see how we are really splitting the power required for the rotor into several components. Only for hover and vertical flight, there is no horizontal flight, because that will come later. Okay. Now, I am going to write everything in a symbolic form, very simple. So, here is this. Cp is Cp climb, power due to climb, and then power for induced Cpi, and then C profile drag Cpd. Okay. Now, the slowly we start the little complications. Suppose first we simplify, then complicate. If lambda c, that means climb is 0, because climb velocity is constant. If you take it out, that is nothing but lambda c Ct, that is all. Whatever is the thrust, if you want to lift the weight of the helicopter in non-dimensional form, just velocity into the weight in non-dimensional, that is your climb power. Then induced, you have to get the induced velocity corresponding to the climb velocity. Please understand, it is not the induced velocity is same as hover induced velocity. That means, we have to learn how to get the induced velocity in climb. Okay. That we will do later. And then this is the profile drag. So, we will write the whole expression. Now, for hover, it becomes, see this integral is what? Sigma CD over 8, that is all. Is it clear? So, I will write the whole thing as Cpi for hover. If I take hover case, power becomes Cpi plus Cp profile drag, and Cpi is nothing but what? If it is a uniform inflow, then this is lambda Ct. So, we can write it as lambda Ct for uniform inflow. Lambda means, sorry, lambda I will put it that, uniform inflow, and this term is, so you will have sigma CD over 8, and I am assuming that CD, that is the profile drag coefficient of the blade, every section is constant, because otherwise that also can vary. Please understand, because if you have different aerofoils, if you have different camber, then the CD also can be a function of span, but for ease of calculation, and CD can be function of Mach number. Please understand, because it is not a constant. Now, in actual calculation, actual means in the industry, you do not use this expression. You calculate, you get the drag coefficient of the airfoil for various speeds, various angle of attack, and then have a table. Okay. It is like a data table, that is through internal test. And then whatever is the local angle of attack, what is the local velocity, take that value, go pick up that CD and put it there. That is how they evaluate, because if you want to be more precise in your estimation of the power, you have to take the correct characteristic. Whereas for the course, because it is easy, otherwise it is very difficult. So, we say everything is constant and we easily integrate from 0 to 1, and your CPI, this is what you are getting, lambda I CT plus sigma CD, I will put it as CD naught or CD, it does not matter. If you want to put a subscript 0, you can put it, because drag coefficient normally CD equals CD naught plus some etc. So, we will take it as CD naught, which is a constant value. So, for this course, we will use constant. But here in writing this expression, we assume that lambda I, that is the induced velocity in hover, is a constant over the full disk. Okay. Then momentum theory has given me lambda I is CT over 2, momentum theory in hover. Okay. Hover case, lambda I is this. That means I can directly put. Now, you see, this is the expression which we got earlier. In the momentum theory, power, when we wrote power coefficient, it is basically CT power 3 by 2 under root 2. That is the ideal power, which you can never get. In the real case, because you cannot say my inflow is uniform, all right, and you will have a non-uniform inflow. And then there are some other swirl velocity is there. Swirl factor, we have neglected it. Swirl in the sense that is actually you are rotating something. So, the flow also will go parallel to the rotor disc, but that effect is small, but still it is there. In propeller, it is, they take it swirled. Even here you can do, but then how do you get the swirl? Again through simple momentum theory. Okay, I will not go into that, but if you want to know, I have it. We have done some calculations for propeller blade for NAL. So, that is there, that report. We correlated with some experiment which was very good. Okay. But in the helicopter blade, usually the swirl takes very less. So, you neglect that, it is a less power. But then non-uniform inflow, all those things are there, that you cannot totally neglect it. So, empirically what is done is, they say let us add a factor, there is an empirical factor they add in writing this power expression because of various other reasons, non-uniform inflow, etc. So, you say this is written as some factor k, this is the factor which additional losses, okay, because slowly you will realize the losses can be due to several reasons, because this k is an empirical factor, but you are adding 15% extra. Okay. What are all the various reasons? You can say that part we will, I will just briefly introduce later. Then this is sigma CD naught over 8. So, now you see Cp in hover is this expression. non-uniform inflow effect, then there is a tip. Okay. The tip is you are integrating 0 to 1, straight away you are taking 0 to 1, in the sense along the full span of the blade, but near the tip it will not be like this. The real rotors, there will be a drop in the lift at the tip, whereas our theory, what does it say? Because lift is some sigma a over 2 theta r bar square minus lambda r bar, that is per section. Now, if we plot that expression, I am just going here, because we took that what? Lift, non-dimensional lift, okay? Lift per unit span, okay? Non-dimensional. If you have, that is sigma a over 2 okay. This is what we had. That means, how this lift is varying? It varies as, so if I plot this unit span versus r bar, it will go like this. This is 1. Okay. Now, you by looking at the diagram, you immediately see that my lift is going up, near the root lift is 0, very close, because the dynamic pressure is small. So, this is there. Actually, the lift becomes maybe beyond 0.5, you start having a large value. Okay. But in actual rotor, this will go and then it will drop. This is theoretical. This is actual, because lift at the tip, because there is no card at the end, lift is 0. So, it has to go and then come down to 0. Okay. Now, this particular region loss, you have a lift is lost, but drag will always be there. Okay. And then your inflow can be non-uniform. So, all these effects, this particular thing I think I gave somebody tip class, someone is supposed to do, it is represented by a loss factor, because if you want to get real load, you can't do by momentum theory. Please understand, you have to use a more sophisticated analysis. If you want to analyze near the tip, it is very complicated motion, because the motion is 3-dimensional, flow will come, vortex will go up, etc. That is why analysis of tip is very, very complicated. As we go along, we will see later. Okay. Now, you have a expression for power. This is from blade element theory, but you need momentum theory always to get lambda I, and this is a uniform inflow. So, now you have this expression. Let us go and write the figure of merit, okay, because you now got the power. Figure of merit, what was that? Ideal power divided by actual power. Okay. Okay. I will flip this. So, non-uniform inflow account for losses. Okay. That means, when I say non-uniform inflow, you must have a procedure to calculate the non-uniform inflow, because simple this momentum theory does not give you that. Okay. So, we will learn about that particular procedure next, but before we go, let us look at the figure of merit expression. Figure of merit is actual power over, sorry, this is the ideal power over actual power. Now, you see, for the same thrust coefficient, if sigma increases, then what happens? Denominator is increasing, so figure of merit will drop. On the other hand, if sigma is small, okay, then figure of merit will go up. But last class I mentioned something, that is, you saw theta pitch angle. If you look at that previous theta 0.75, right. Last class I wrote here figure of merit Ct power 3 by 2 over root 2 plus sigma Cd naught over 8, right. Now, let us look at the kind of paradox or contradiction which you get. If I want a high figure of merit, same Ct, it is fixed, that means sigma must be small, solidity ratio, that means NC over blade area over disc area. But when I go here, if sigma is small, then what will happen? I need a higher pitch angle, but higher pitch angle if I keep on going, then I may land up in stall. So, now it is a compromise, you have to decide what sigma I should use. Okay. If you look at most of the rotor blades, okay, you can calculate, because if I will give you sigma value, I think I have some for the ALH blade. Okay. I will just show you that this is what the curve for. I have essentially plotted this figure of merit curve for some values. Now, you can see figure of merit increases with Ct. As you increase, initially it rises very fast and then it slowly tapers, asymptotically it reaches 1. Now, it also tells me, hey, if I have a high Ct, that means my thrust coefficient is high, I will have a good figure of merit, because the denominator, if I keep on increasing the Ct, okay, this becomes very small. That means I must have a rotor with a high Ct. You know, earlier it requires high power, because high Ct means I need to have a lot of power, because you know that lambda it takes. So, this is the figure of merit curve alone. If you look at it, it will give you a set of result which you say, I should choose like this, but then actually you will find that whatever you decide based on figure of merit alone will become detrimental to your rotor, because in your operation, because one is, if I keep on increasing, if I decrease sigma, I know that my pitch angle is going up, but if my pitch angle goes up, that means my blade may stall. Okay. So, I cannot make my sigma very small also, just because I want to have a higher M. Okay. So, this is that is why that figure of merit is used only as comparison of two rotors having same Ct. It is like same disc loading you try to have, and then see which one is a better in terms of the efficiency of power required. So, it is not that I keep increasing my Ct means, then you will go. Most of the helicopters, you know that Ct is in this range, it does not go to 008, 008 is very high Ct, 01 is too high. Okay. So, it is always in the range of not 5. Please understand, when you look at all these numbers and Cd naught, profile drag of the blade, you may take it as approximately 0.008 or 6, or sometimes if you want to have a slightly higher value, maybe 0.01. So, please understand, most of the numbers which we are dealing with here are small numbers, okay, in the non-dimensional form, but this is to give you an idea of how you can estimate the power in a very quick calculation, hover power, because you know that initially I showed, as you increase the forward speed, the induced power is decreasing. So, automatically you say, okay, let me take the hover condition for my power estimate. Of course, high speed, it may again come to the same value. So, these things give you a quick estimate, but please understand, these are all very good, in the sense even in the industrial calculation, that is where the designers, the good designer who knows the basics strong, he won't do very detailed calculation with a computer program. Yes, you do it, that is for actual estimation, but he will know by simple calculations, okay, your results should make sense. If they do not make sense, then means there is something wrong in your actual calculation, in the very detailed thing. So, that is why it is very important to understand the various expressions, thrust, inflow, figure of merit, theta, Cp, etc., all these terms. Okay. Till now we have learnt about the power and thrust for a rotor in hover and using uniform inflow. But now we will learn about how to get non-uniform inflow. Okay. And here, just for a reference, I took a realistic rotor, sigma you see, n number of blades 4, 0.5 is the card, okay, radius is 6.6. So, pi r, NC over pi r constant. Okay. Now, this value is about 0.096. Only one particular rotor has a value which is about sigma 0.13, which is a high sigma, okay, not all, most of them will be around, and I use the value lift curve slope as 2 pi, okay, and I am using this expression to give you, if I vary my Ct, how my pitch angle of operation changes. If it is not 4, it is about 6 degrees, but please note all these are in radian, then you have to convert it to degree. Okay. This is just a simple calculation which I did, because when I give you a homework, you have to do that, and not 5 about 7 degrees, go 10 degrees. Now, you see, when you are preliminary design, when you are making, you do not go and then make a high operational angle, because if you do it, actually when you build it may be still more, and you may start having blade stall, more drag, more power. So, you try to operate always around 5-6 degrees, okay, 5-6 degrees operation, but actual calculation you also will go about 8-9 degrees in the hover case. That is a detailed calculation I have. When you make in hover, pilot gives a pitch angle of about 8 to 9 degrees to the blade. You do not go and give 20 degrees or something like that, okay, because in forward flight then you have to consider certain time varying angle, and then you may have stall. So, all these factors come into picture. So, we have learned just now very simple hover. Now, another important thing which before I go further, I wanted to tell you is, we use the word, okay, uniform inflow. First is how do I get, another I said non-uniform inflow, then you will say how do I calculate. because uniform inflow you simply assumed lambda I is root of Ct by 2. Okay. How will I achieve? That is the first question. Second question is, you say there is no uniform inflow, you will have only non-uniform inflow. That means how will I calculate the non-uniform inflow? So, now we learn about how to calculate the non-uniform inflow. Okay, I think I have some numbers here which are some kind of comparison before I go, just for comparison, okay, before we go to the non-uniform inflow. One is a ALH which is about 4000 kg. This is Me 26 which is about, you see, takeoff weight, number of blades 8, main rotor diameter 32 meters. Please understand, it is about 100 feet, okay, maybe from here to there, main rotor diameter, maybe more than that, I do not know, all right, because I do not know, this will be what, 50 feet, one card, one blade, and then rotor RPM 132. Okay. Now, you see the tip speed of both these helicopters, the weight class is totally different. Okay. Why I want to introduce here is so that you have a appreciation of the numbers in non-dimensional form, but industry for comparison, yes, but then when you actually design, you can't tell your manufacturer, okay, I want a non-dimensional thing of this. No, you have to give actual dimension. So, you need to know that number also. Tip speed is 217 meter per second, 221. Solidity, see this is 096.12. Thrust coefficient is a high. And then lambda inflow, lambda is a hover inflow, and then the figure of merit fairly close. Even though the rotors are of different class, different weight, everything, but when you look at the non-dimensional numbers, they come reasonably, they fall in one area, okay, in the non-dimensional level. This is just for information only, because you can collect the information from any two helicopters and then start comparing them. Okay. So, if you collect several helicopters, then you will be able to have an idea of how these numbers will. Okay. Now, we will go to the non-uniform inflow calculation. I have written final expression here, but we will describe it very systematically. I will go through the derivation here, because that is important. See, what we have is, this is called differential momentum theory. You may ask whether it is valid, that is a different question. You take the rotor disc, now take a annular area, at a distance lowercase r and with a thickness dr, okay, delta r. This is my annular disc. What I will do now is, I will start comparing the thrust generated by this annular area using momentum theory and using blade element theory. Please understand. You may ask, what is this momentum theory? You said it is for the entire disc. We used a slipstream, and then we assumed that some uniform inflow everywhere, we calculated, we got the expression. Now, I am saying, as though the slipstream consists of several concentric cylinders with a different radius, okay, and I take a small elemental area of the rotor disc, I neglect everything else. I assume this particular annular area is not affected by either the flow inside or outside that. This is an assumption. Please understand, this is an assumption I make, and I simply blindly, please understand, I blindly use momentum theory. There is no logic in this. The logic is, finally it matches very good with real life situation, that is all. If you want to do very detailed, so that is why There are several people come up with ideas. Okay, it's like this. Momentum theory is based on energy. You simply apply, instead of over the whole disk, I take a small region, I apply over only that region. Okay. That means what? That region you have isolated from the rest of the things, and you assume that nothing is, that is not affected by anything outside. This is an assumption you make, and then you simply start using it. Now, the proof, what you are doing is all not correct, comes if you get the result. If it does not match with the experiment too far away, then you say, okay, this assumption is not good. But if you find this is much closer, it is reasonably good, then you say, oh, maybe this assumption is fairly good. Okay? And that is how otherwise you have to do, I told you, vortex theory, prescribed wake, free wake, vortex theory you do. Even there are approximation in that theory, but that is a little bit more physics based, I would say, because you say, I say there is a vortex strength and then try to calculate the strength, whereas here you simply apply what you did for a whole disk to a small area. Okay? That is the first assumption you are making. Then you will get from here, see now we will go step by step. If I take the blade element we know that lift per unit span. Okay. This is due to all the blades you have to take, okay. That is N, essentially half rho omega r, because this is what? Dynamic pressure chord lift curve slope into theta minus up over ut into sorry, per unit span. Okay, I can eliminate this. Okay, per unit span, this is the lift which we derived earlier. I can non-dimensionalize this. If I non-dimensionalize, I am going to get that expression which is written there on the other side of the board. Okay. So, I will get dCt, because you divide rho pi r square omega r etcetera, then you will get lift per, that is dCt. This will be sigma a over 2 into r bar square theta minus lambda r bar, but this is not per. So, you have to take the dr bar, okay, because this is the thrust developed, elemental thrust developed over dr bar due to all the blades, that is why sigma comes in. Okay. This is from blade element theory, got it. Now, you say momentum theory. Momentum theory, we are going to now use differential thrust, dt. This is, I will write momentum theory. Okay. So, this is, please note, this is from blade element theory, what we got. Momentum theory, differential, I am going to put differential. Okay. What is my area? Area is 2 pi r dr. So, I am going to get differential thrust is, if you go back your equation, momentum theory, we wrote thrust is equal to mass flow rate. Okay. So, we wrote 2 rho a, this is for hover. Okay. If it is climb, then you will have mass flow rate will add the climb velocity also. Right now, let us take it only for, because I have used the climb also here. Okay. If you add climb, then this will become 2 rho area of the disk V plus nu, because this is the rho A V plus nu is the mass flow rate, okay, because the climb velocity plus the induced. This term is the mass flow rate, change in velocity is 2 nu. This we will prove it in the next class. Okay. This is how I write my thrust. Now, I am saying this is this expression, this is for hover, this is for climb, okay. Hover and climb. You may call it global momentum theory. Global means I take the entire area of the entire disk. Now, I say, hey, I am not going to take the entire area, I take only the annular area. So, I will write here 2 rho V climb plus nu into nu. What is my area? 2 pi r dr. Okay. You follow what I have done? And this is the differential momentum theory. Now, you may ask, actually I will tell you now, why I have to take the annular area? Why can't I take only a small r dr d theta? Okay, you can, well, you can do that. Actually, that is used in industry if you want even the azimuthal variation. That is again an assumption. That is all these are very simple assumptions you make and then try to get an inflow value. Now, you have an expression for this. You can non-dimensionalize this divided by, as usual, rho pi r square omega r square. If you non-dimensionalize, you will get dCt. This is from momentum theory. You will have dCt will be, because you have 2 and 2, you will have 4. Okay, I will write that 4. This term is lambda, because Vc plus nu over omega r is lambda, and then this divided by omega r is lambda I. Okay. Then r bar d r bar, because non-dimensionalized rho pi r square omega capital R whole square. Now, you see I have 2 expressions for the differential thrust coefficient, one from blade element theory, one from momentum theory. Okay. Now, I simply relate means just equate both. Now, you see this lambda is, you know that this lambda is lambda c plus lambda I. Okay. And here you have lambda lambda I. Equate both of them, then collect all the terms. Okay. Now, let us see, when I equate, I erase this part. Okay. I erase this completely. Then I will write this, after that we will go to that. So, you will have 4, this lambda I am using it as lambda climb plus lambda I r bar dr bar. this is equal to, you have your sigma A over 2 r bar square theta bar, sorry, r bar square theta minus r bar lambda c plus lambda I d r bar. Okay, cancel out. Okay. Then you will be left with this simple equation, which is 4 lambda c plus lambda I into lambda I equals sigma A over 2 r bar theta, okay, minus lambda c plus lambda I. Okay. Now, this is nothing but a quadratic equation in lambda I. So, you will write this as 4 lambda I square plus lambda I 4 lambda c plus sigma A over 2 minus sigma A over 2 theta r bar minus lambda c equals 0. Okay. This is a quadratic equation in lambda I. Now, you see the interesting part. This is the induced velocity, and I have the local blade angle. Which angle is there? Okay, and number of blades is there, lift curve slope is there, all these factors are there. That means, if I solve, you write, because this is a quadratic equation, you can write lambda I equals minus all those things, and that is what is given here. Okay. All right. So, you can note down this expression, because this is the now you see minus b, this is the term, plus or minus root of b square minus 4ac, okay, divided by 2a, and then you divide by that factor 4, etc., you will get that expression. But you know that minus b plus or minus, two roots are there. That minus root, then you get a negative value for inflow, which you cannot have. So, from physics you say I must have only the positive value for the root, all right, and that is why you put only the plus sign. Is it clear? Now, this lambda I, if you look at it, this is a function of r bar. That means, depending on my span location, inflow can vary, all right. So, this is the, please understand, this is a powerful expression, in the sense it is widely used in the calculations, even in research, even we use this. Okay. This is a very, very important expression. We do not use the uniform inflow usually. Uniform inflow is too gross an approximation, but it is good, it is all right, it is easily you can calculate and then show, but you always take non-uniform inflow through this expression. Now, I just want to reduce this, this is with the climb. If I make lambda c 0, automatically the inflow in hover. So, is it clear? Because that is how the quadratic equation is solved, and then you get the root, this equation you get that value. Okay. Now, let us write just for hover case, that means lambda c is 0. here lambda c is 0, lambda c is 0. You will get lambda I, okay, is, you bring this term first, because lambda c is 0, lambda c is 0, everything is 0, that is why you will have sigma a over 8 is a common factor. You can take out that 16 also, that is all right. So, you will write that, that is simplified, lambda I becomes minus sigma a over 16, this is the first term, and then the second term becomes what, sigma a over whole square plus over 8 theta r bar, right. Now, you take out sigma a over 16 outside, that means here you are essentially multiplying by 2. When you take it out, you will get, open a bracket, put this term first, this will be 1 plus, because sigma a over 2, what is that? When I take out square, I will be left with one more term. So, that term will become that 32 over sigma a theta r bar minus 1, okay, because that minus 1 is, this is the term, okay. Now, you look at your, what, is it clear? Now, what you do is, you see my inflow is a function of angle and r bar. If I want lambda I to be constant everywhere, then if this quantity is a constant, constant means uniform inflow. So, I will say for uniform inflow, if I want, I need, that is lambda I is a constant, that means theta r bar should be equal to some constant. So, theta r bar equal to some constant, okay. This you write it as, because when r bar is equal to 1, that is the tip. So, the constant is nothing but the tip. So, your theta becomes theta tip over r bar. This is the ideal twist. Now, you remember earlier I mentioned why that twist is, if I have this kind of a twist, because r bar is r over capital R, okay, I will get uniform inflow. You follow? Now, okay, if I get uniform inflow, so what? Okay, that is another question. Okay. Uniform inflow helps. If you go here, if I substitute for that particular expression, okay, let us, oh, I have to get that thing. I just want to relate, because there are very interesting ideas in this. Okay. This is a non-dimensional lift. If I write it non-dimensional lift, I may, or you can put it dct also, it is okay. I think dct becomes, okay, because this is not a non-dimensional, this is now dct is this. If I substitute theta as theta tip over r bar, then what will this become? This will become theta tip r bar, one of the r bar will cancel out, right, and here lambda r bar. So, I will have lambda r bar. Okay. Now, what is the area of the annular disk? Annular area is 2 pi r bar dr bar. That means, I am saying lift per unit area, okay, or thrust per unit area. Okay. You can call it thrust per unit area. Area is a non-dimensional, please note I am using non-dim, okay. Non-dimensional thrust, this is the thrust. If I divide by 2 pi r bar dr bar, that means what? R bar dr bar will go off, and this is a theta tip, and my lambda is uniform inflow, right. That means, I get this for uniform inflow non-dimensional thrust per unit area, or in other words, this is a which means my loading, I distribute the load uniformly. Please understand, because it is not that some area I load more and some other area I load less. It is like my entire weight of the helicopter is uniformly distributed over the rotor disc. In other words, equal area support equal weight, okay, which is a good design, because you do not want to put some heavy load in one place and very lightly loaded in some other region. So, you see the uniform inflow has lot of implication. That is why you have to try to achieve that uniform inflow. In the earlier days, people were not making a twisted blade, okay, but nowadays all the blades are twisted blade, but of course, they are all uniform cross section, because from manufacturing considerations, most of the blades are made uniform cross section. Okay. Now, you see this is the ideal twist, but manufacturing ideal twist is a bit difficult. Okay. So, you now know, hey, I am not going to take the twist till r equal to 0. So, I stop at maybe 20% of the blade span, I stop, because my aerodynamic section usually starts around 0.25, okay, 0.25 of the radius. So, I can twist only up to that point. Okay. Now, that is why you now know why that non-uniform inflow calculations are done, and from there only you can show this. Okay. Uniform, why, what type of twist, ideal twist, otherwise this is the proof. But then for this proof you need blade element theory, you need momentum theory, that is differential momentum theory. These two thrust you equate and then get the inflow, put it there, you see, okay, if I want uniform inflow, my blade must be twisted. Okay. This is all for hover, please understand, this is all for hover. Okay. There are certain other important points. I will just briefly mention two of them now before I leave you. I mentioned that the tip region, the lift as what we saw, it goes like a parabola to the tip r square, but then near the tip region the lift is actually 0, it is not a high value. So, there is a drop. Now, there is a correction you have to give. This is called the tip losses, tip loss, because the flow is going to be 3-dimensional flow there, because even if you take a vortex, then it will go up. But if you really want to precise calculation, you have to use a vortex theory. Okay. But earlier Prandtl formulated, he used a 2-dimensional vortex wake, because number of blades become important, because the tip, how the wake will go, how many blades are there, okay, everything is important. So, he made a theoretical calculation, and then he came up, there are several people used different derivations, I will not go into the details. What this final conclusion of that is, instead of integrating that lift dr from 0 to 1, do not go to 1, you go to 1 is actually non-dimensional, b. B is a tip loss factor. Okay. Because somebody I have given this he has to, B is tip loss factor and it is less than 1, which is what is the value is. They found that if you use a factor B equals 0.97, okay, for the lift part, drag part you take it till the end, but you integrate your lift only up to 0.97 of the radius, do not integrate till the end. They find that this expression is good, because that lift whatever you theoretically predict is very good. And now industry uses, most of our calculation also, we use tip loss factor. But if you really want to do a very detailed tip, because for those who are interested in aerodynamics, you can take the real tip and you can do a line vortex or a sheet vortex, okay, and then really calculate that quantity, because the flow near the tip is very complicated, because it gives to noise, it gives to drag, there are so many other factors. But now industry uses different aerofoils, because near the tip they do not use the same aerofoil, they try to use a thinner aerofoil, because the drag will be higher. So, to reduce the drag they make a thin aerofoil near the tip, but that tip section if you really see 0.95 to 1, only in that zone they will change it, rest of the section it will be same. Okay. Now, the research part of it is essentially refining further and further your analysis capability and improving the performance of the rotor. And there is one, which is the best tip, there is no answer today, because I can quote from one of the person from industry, he said that there is no optimum tip, till now nobody knows, every industry uses its own tip, because they will not give any details out. And there is one which is called I think Westland, they put a burp, some British experimental rotor program, that is called a burp, BERP. Okay. That tip, if you see the blade, it will be like this, the tip will be like a paddle, something like that, in a very funny form. Some people may use like this, some people may use like this. There are a million types of tips, but now if you want to really do for every tip experiment, okay, it's good. Actually, I thought that we have a test rig, we should be able to manufacture different tips, shapes, just make an attachment and do it. This is like a future research, because then you will have your own wealth of data to say what tip is good, but then predicting that with your analysis, that is still, the gap is quite a bit. Okay. If you want to really go to fine values, otherwise gross values I am telling you, otherwise you will not be able to fly the helicopter. We make a lot of assumptions, but still the mean values. Okay, what is the thrust? What is the pitch angle? That is all, whatever. This simple theory is good enough for you to give all those things. That is why helicopter flies. Okay. But if you go to more complicated things, I want to improve, then more detailed study is required. That is why tip loss is one. Another one is root cutout. Okay. I have put only here, I did not put. The blade airfoil does not start from 0, because you have a hub and your blade root section will be something like this. Okay. Because you have to take it, put a bolt, attach, etc., and the hub will come, and the aerodynamic section will start only after some distance. That means all this portion there is no lift, you will get only drag. Okay. Now you have to take that also in your calculation, but in all our calculation, because it is easy, you integrate from 0 to 1, 0 to 1, it is easy, you write an expression and everything is compact, which is good. But for a little better calculation, more realistic calculation, I would say, you take a root cutout, and the root cutout you call it as some E, offset. You can call it root offset. Okay. So, this is the root cutout, this is the tip loss factor. Okay. In calculating for thrust, drag, you take the everything. Okay. Is it clear? Now, I think I will send you one assignment, because I am preparing it, I will send by email. You make calculation. I want you to generate, I will give the data, only these equations, there is nothing more, but for a rotor. Okay. Then you plot the graph how they vary with the various twist expressions, but you have to trim the helicopter. Trim means CT must be balanced. So, you have to do some iterative calculation. You have to write code, but do not copy. One fellow writes, everybody prints, but I want finally the figure. Okay. Now, since you asked, I will show you one diagram. This is the curve CQ. CQ is CP, okay, torque coefficient, CQ over sigma. This is CT over sigma power 3 by 2, because that expression, what was that we had? See, you had CP is CQ, which was CT power 3 by 2 root 2 plus sigma, right. So, you divide by sigma. If you divide by sigma, this will be and CD naught over 8. If I plot CQ by sigma and this by sigma, this is a straight line, CT power 3 by 2, and this line is this line. CT by sigma power 3 by 2, this is 3 by 2. No, this is an error, that is all, it should be okay.
Does this mean that we cannot compare aircrafts with different helicopters with different solidity ratio? Figure out the rest.
Usually CT, you compare rotors of similar class. Rotor means similar weight class. Do not write fully from, but even then we compare two helicopters with a different weight class. Figure of merit is not treated very seriously in actual design. Of course, if it is below 5 or 0.5 or another thing, it is a bad rotor. Solidity is very important, because solidity gives you, I told you, Ct by sigma. Ct by sigma is blade loading, which is also blade pitch angle. Okay. That is why simply saying sigma does not make much, but saying Ct is okay, because thrust coefficient, that means am I in the helicopter class, because it is usually in the range of 0.005. But Ct by sigma, sigma by itself, if I give you, you can take a propeller blade and give a sigma value. Okay. It does not specify whether it corresponds to a helicopter or a propeller or something like that. Okay. But Ct by sigma, that is why Ct by sigma last class also, that is the, it has so many meaning. In the hover case, you know that it is approximately the pitch angle. Okay. Now, if Ct by sigma keeps on increasing, that means what? The mean pitch angle you are increasing. Mean pitch angle increase means you can increase up to some point, after that blade is going to stall. Okay. That means you can go up to that Ct. Suppose you design a helicopter, how much, because you do not design only for that particular weight, even though you design for 4000 kg, sometimes you may have to carry a little, the capability. But this factor in hover is, yes, you are related to stall. Same thing can happen to forward flight also. But if I simply represent Ct by sigma for a helicopter, Ct is fixed, because the weight is known, rho pi r square omega rho is known, sigma is known. That means Ct by sigma cannot vary for a helicopter. Please understand. But Ct by sigma as a parameter, if you say non-dimensional, that is the blade loading or indirectly pitch angle. Hey, what is the capability of the rotor? How much Ct I can really take it before the rotor becomes, one way is stall, another way it is vibrating. There are several factors. Another one is a hub load increases. So, you can set various criteria and you take the rotor, and then you say I am taking it to the extreme of the rotor, because in internal you can do. Keep taking to the extreme and you say beyond that my pitch link, because this is how it was defined. They get the pitch link load, because the pitch angle is moving, and the pitch link load is directly dependent on torsional moment, because when the blade stalls, torsion moment comes. This is a dynamic load. Please understand, dynamic stall means it is oscillating, your oscillatory load will increase, which is related to fatigue life. So, they say, hey, where will I start having large oscillatory load? Now, large means what large? Now, you have to define some number. Okay, I have my limit of infinite life in metals, and then I will say 3 times the oscillatory load. If I get at some situation, that means I have reached my limit, I cannot go beyond that. So, this is how they try to come up with some kind of a limit of the rotor, because in certain operations Ct by sigma everything, but the pitch link load will go up to such an extent, then pilot will not be, and sometimes the vibration will go to high value, he will not be able to operate the vehicle. That is why it is very interesting to see, because this is based on my discussion with the industry people. What is the best helicopter? Okay. How do you say a helicopter is best, or rotor system? He said that if my operation is limited by power, then it is the best helicopter. In the sense, hey, I do not have engine power, that is why I am not able to fly more. Otherwise, everything is wonderful. But invariably, please understand, most of the helicopters, it is not restricted by power, it is actually restricted by suddenly vibration will increase at some speed. Beyond that, you have to sit in a helicopter to see the vibration. Okay, I am telling you, the noise will go up, pitch link load will go up, pilot will find it difficult to control. Even though I have power in my engine, please understand, I cannot take the vehicle beyond, because I can't control the vehicle, vibration is very heavy. then you say, hey, that is, so what sets the limit is not the engine power, it is other characteristics really is setting the limit of your helicopter. You follow? And this is where still problems are there. It is a very challenging problem, you will see, but it is really beautiful. So many factors you have to consider. You say, hey, I am everything I can satisfy, so I can fly. If you give me more power, I can take it. So power restricted helicopter is the best helicopter, but invariably it is the other restrictions which will set. You can't go beyond this speed, because beyond that speed if you go, the whole thing will shake like hell, because you have to sit there. Because I once went, I sat in a production, your window pan and everything, you can't hear anybody inside, because the pilots talk to them only through wireless, even though they will be sitting by the side. Okay, noise is terrible. That noise you have to open and then hear it, because I couldn't put, I came out for about, I would say 2 to 3 hours, I did not hear anything, absolutely nothing was, it's nothing, you don't hear. And then the vibration, if you see the whole side fuselage panes, they were vibrating of this much amplitude, this much. That means if it is here, it goes this. You think that because if you are, because you are an academician, the whole thing is going to blow up, it will take off. That is the level of vibration. Now imagine, it is not the power. Power is there. If you want to fly, but if you fly, you will blow the vehicle. So these are restrictions which will come up. So you have to make sure I reduce these things. Okay, I think with this we will close today.